So my name is Jaebom. I'm working in discrete mathematics with Charles and Karen here. So today I'm going to talk about the graph and network, probably giving some overview with some of the new things we are having in new version. So I'm just going to start talking about how to build graph and then some computation analysis, visualization. Kind of looks similar to previous talk, but I say we didn't copy each other. We just ended up having some same structure. We were working together for a long time, so so deja vu. So first, to working on the graph, unit graph. Right? So first way, like in geometry, we can import from the existing the graph format. For example, here like a GML graph. So you can just using the import function in the Mathematica, and default will be just giving you the graph. And there are various attribute you can extract out of the graph format. It depends on format. They usually not all the same, but in this case, you can say like get the adjacency matrix is directed or not, and graph, and then some graph attribute like its label directed, something like that. And here is list of graph format we're supporting right now. And then we are keep adding more and more if there are requested by user or if we find something useful. Also, another things we are working on is we try to improve the performance of importing and export. I think even in version 13, there are several the graph format that improves performance-wise. It's much faster than before. And there is not always the data is following the graph format. Sometimes the people using their private format, fortunately, they usually come with their description. For example, here, one of the example from, I think it's from Stanford, the database. And then here's how the data looks like. You just have some description directed graph. And then in this case, I just follow the description, extracting this pair, which represent the edge and the construct graph. Another type is the CSV, the table format. And then if you just see how it looks like, it's just, in this case, we just need to first and second, source and target. So I just grab it, and then as you know, this is directed. So I just mapping the directed edge over it to construct directed graph. And also we see there are way, so we can also extract way information and then assign the way to graph. And then this is how we do. Another type is, this is one ADJ, adjacency matrix. So this data actually specified adjacency matrix. So 2, 1, 1 means the position 2 by 1 has element 1 inside the matrix. So we just parsing that and supply to sparse array, which construct adjacency matrix called adjacency graph over it. Then we got the quite sizable graph here and can do computation after that. And we have like a curated data inside of Wolfram language and Mathematica. So for example, here we have almost like over 190 collection, the empirical network. So for example, she's Lemaitre graph network, and also you can get the long description, or it has several elements inside of it. You can check. So if you see the byte count, description, those things. And then another thing is resource data. So Charles already mentioned about resource data is public, and then the good thing is you can also adding your own data, share with people. So if you have nice graph data, then I encourage you to, adding into resource data, sending your data that people can use. So here's one of the example, Marble Universe Social Network. So here's summary of data. So it has like 19,000 vertex, 96,000 edges, and it's Marble Comics character collaboration network. So let me just, after getting it, you can modify the graph to get something more interesting graph. In this case, let me just show some step. So first of all, I just checked the connected component of this marble network. So you have see the one big chunk, and then there are some smaller networks. So I just take the first one, connected component. And then if you see how the vertices relation each other, so the neighbors of comic vertices, the vertices has two types, comics and hero. So there are relation between comics and hero if the heroes appear in that comics. So like this one, this comics, the name of comics, and this is name of hero. So it's form nice bipartite graph. So when you have bipartite graph, you can usually extract projection graph, which containing just one part of it. So for example, right now I'm gonna take the hero projection. So what that means is vertices will be hero, and then relationship between the hero if they are showed up in the same comics. So I just taking, in this case, fortunately we have annotation value, same type. So I just getting comic type, and then taking hero, and then do some subset or blah, blah, just getting relationship. And then I'm gonna only select, so there are the heroes that appear many comics each other. And then there are hero only showed up several, only one or two comics, which is sad. But I just gonna take the heroes that showed up more than 50 times in the comics. So you got some little bit decent size of graph then. So for example, like here, this is the selected small marble graph that each other appears more than 50 times in the same comic, in the comics. And I just replace vertex to the name. So vertex of this network now the actual hero name. So we're gonna work with this graph later. So after you get the graph, okay, before that, do the computation. So here's just modeling. And also what we are working on is modeling graph and then editing also. So there are like core computation you can do over the graph, like a vertex delete, vertex contract. There are several functions. And then like those functions, we are just not stopping. We keep trying to improve performance because those are real core functions. Many graph operation can be, decided by that performance of those functions. So for example, vertex contract, we dramatically increased performance in upcoming version. So you can see if you are working on the function, you can see how the difference between those difference of that function compared to 13.1 and 2. After that, once you have a graph, then you want to do some computational analysis. So here's in case of social network, the centrality measure is kind of big thing. So if you attend food network, the talk people charts in this room, then you can see the edge connectivity measurement and degree centrality, all those centrality, how it used in real life situations. So this one actually very useful to measuring importance of vertices, depends on criteria. So for example, like here's some of famous Medici family graph, and then I just highlighting some importance to vertices, the family, depends on the centrality. And then there are another measure, transporosity and transitivity. So it's a local clustering coefficient actually measuring how the neighbor of vertices they link to each other. So this is the just histogram of this internet network. And then another measure we can do is like homophily, associativity mixing. So here's an example of using the friendship network in Leish. So this case, you can compute the graph associativity. So this is what it is. Highly social student are friend with other highly social student, which can be expected. And this is the value for that. And then graph associativity by Lace. And then you can also find out some group, some substructure of graph. There's some like clique, K-clan. So here's the small example of it. So you just get the slash dot network from Stanford database, and then you just compute some basic subgraph structure or structure. So weakly connected graph component, strongly connected component, so edges, so clustering coefficient, etc. And then you also do some statistic analysis over it, conjunction with some statistical functionality in Mathematica. So here's some brief example. So you have graph, and then just getting in degree, and using the estimate distribution, we can estimate the some parameter of log normal distribution. Also, you can try to estimate parameter for Pareto distribution, and this one is its own distribution. And then you can just compare it. So you can just basically see, seems like, oops, let me. I think I missed some evaluate something. Oops. Sorry about that. Well, just, okay, here we go. So like here, Pareto kind of looks similar to its original the distribution. So there's more things you can do with the statistical analysis that didn't show up here, but yeah, just go check it, the documentation, and you can see lots of functionality over there. And then there's something new, Graph Plus. So as you can see, the graph you can view as the matrix or adjacency matrix. And then advantage of that, many algorithms, graph algorithms actually using the adjacency matrix, so linear algebra. So actually the BLAS, there's BLAS, the library or API in numerical analysis, numerical computation, which usually good for dense matrix. And for graph, in most of graph real life example, it's actually sparse graph instead of dense graph. So there are lately there's working on those type of matrix operation. So this is one of that called Graph Plus, the API. They're giving the some of building block, the operation over ring structure. And then it's kind of fast, and then very kind of abstract. So the operation is not just plus and the multiplication. You can do whatever you want if it's building the ring structure. So here's one of the example, like here, the breadth-first search, one of the famous graph algorithm. So you can just go in follow to the edge to the next level, but also there are another version of matrix operation. So here is you have adjacency matrix, and this is kind of column vector, the specifying starting point. By just operation on it, you can find the next step, like a 1, 3, then you got the 2, 3, 5, like a 1, got to 2, 4, 6, actually 2, 4, 6, right? To the letter dot. So this is one simple example how the actual graph algorithm related to linear algebra. And we are trying to integrate this graph Plus into Mathematica right now. So one of the example here is, so Graph Plus, and then there are also a library called LaGraph. That is the collection of algorithm building using build by using the Graph Plus. So here's the example of page length centrality. So here, this one is the performance of current method we are using, and this one, this first one is the LaGraph performance. Second one is performance we are currently using in Mathematica. So you can see this one is slightly faster, but if graph is getting larger, the performance difference is dramatic. So usually if your graph is big enough, then using the Graph Plus, you can get the better performance. But this is not for every algorithm. We have to fine tuning and then find what is the better. Certain cases, we found out current method is faster than Graph Plus. So that's something we are working on here. And then, for example, like here, social Marble Universal Network here. This power method is what the method we are using right now. And then this is LaGraph we are plugging in. Then you see it's kind of Yeah, 3 times faster. It's more than that. Yeah, it's quite faster. So once we put this into system, the user probably don't know which one is running. And what I mean is we are automatically detect graph. Depending on the size, we automatically call lograph or the original method we have, or user can specify which method they want to. So there's something, the direction we are going. And then another new thing we add, also we are also adding new function and also improving current existing function. So this is one of the improvement. So we adding kind of different output type for find shortest tour. Also, you can see the starting and ending. Now you see something not indexed. Originally, we only allowed to put the index. If you have the list of something, the starting should have to be index of this list, like first position or by position. But instead of doing that, you can actually specify the element as starting and ending point. So for example, here, and then your return will be just element, not the list of indices, the ordering actually. So in this case, you can just directly call GeoPath to draw GeoGraphics. And also here's the type of output is support. If you say all, then you got the element, indices, which is original output, and then length. So last one is the visualization. So the first thing when you do the visualization, you need to know the position of vertices. So there are 2 ways to specify it. First, by specifying vertex coordinate manually. So this is one example. So your chemical data with a J-search matrix and also chemical data commits the vertex coordinate of this data. So I just specify using it. And also you can use the graph layout. So we have several layout algorithm built into it, and then we can keep adding and improving it. So one of the new, not in 13.2, or maybe next version, is like a layer digraph embedding. In general, it's not, there are many overlap between the vertices when you do layer digraph embedding, especially when you specify vertex size. So new option we are working on is like vertex sizes, then can be changed later. So specify actual box sizes, and then when you try to compute the layer digraph embedding, it account those sizes specified. So try to compensate those things, and you can see there is no overlap anymore. It's kind of convenient. And then styling vertices. So basically just vertex style, just changing color, the directive you can specify as a vertex color, or you can change the shape function. So this is the just example of some predefined shape function, or you can specify your own function. And vertex shape is actually just shape. That means you can put any mathematical expression as a shape. So like a graphics or images, and then like a 3D graphics. So anything will work with vertex shape. So this is one example of vertex shape function. Because of function, you have input form, center position, and then the size of vertices. And with some dynamic, you can do something like this. So you can do much complicated thing or simple thing based on your usage. And edge style, same, just type of edge and edge label of edge shape function. Also, we come with predefined edge shape functions. There's many collection of it. And also you can specify your own function like this. This one also getting the input here and something like that. Okay, and next. So plotting is giving the overall style of graph. By just plotting something, then you got this different type of graph very easy. This easy function, easy option to use. And also highlight graph. This is for use for highlighting some sub part of graph. So here you can also using the saying like graph highlight style with D or diamond or whatever. And this kind of tool probably you don't see this in current version. This is something new graph style we are working on. So hopefully you can see soon. So here's the example of styling the graph. I just using the small marble graph we constructed before. So we just taking top 3 vertices to emphasize it, and then setting up using vertex label style, whatever, and then you have something look nice here. So we have 3 main vertices that has most degree. It turned out to be Spider-Man, Captain America, yeah, it's expected. And also you can do some dynamic. So here's another Facebook data from Stanford database. So I just make one big manipulator so you can check some importance vertex theory, close centrality, and some feature, because this data set comes with feature for each vertices. So this plot actually showing those feature, and then some summary of graph. And color, this is right now color is by the centrality, but you can also color by the circle, because circle means this Facebook data have some circle attribute that I don't know how they define circle, but it's kind of grouping. So I just put the coloring based on that grouping, and you can check the another data. You see. So this is some visualization you can do. So graph plot, actually this plot function, the one main difference is output will be the graphics. So if you do random graph, so this is one of the things, like here it's not showed up because we have some threshold is if edge or vertex count is more than some number, we don't show up. We don't show that because it's kind of too big to show. But graph plot actually, just try it, ignore the threshold. So sometimes you need it. Or you can change the system option, the increasing threshold, but this is one easy way to plotting the large function. And graph plot 3D, just plotting 3D space. Layered graph plot, layered graph plot 3D, actually layered within the 3D space. And tree plot for tree graph. And community graph plot that show the community structure of graph in the plotting. Oops, I think I got in the wrong version. Let me just briefly show this in the different version. Sorry about that. Yeah, this is like a structure, community structure of this graph. And then we have graph value plot. This is still working in progress. So this one help you actually plotting the various the vertex property. So this case, eigenvector centrality is just coloring based on this one. And then Hasse graph is some new function we are working on also, giving the construct graph based on partial ordering, and then graph value plot over it with that to see the like layer. So this is, I think it's time is up. It's all so far end of my talk right now. So we currently we keep improving the graph functionality. Also, one of the direction we have right now is for large graph. One of the effort is you see is like a graph plus, which is good for large graph computation. Also, we are working on to integrate some neural network, GNN, or graph database. That's another thing we have in plan. So yeah, that's about today's talk. So thank you for attending.